Hello and welcome back to LFI Debates. In our physics class today, we'll be discussing about some optical instruments like microscopes and telescopes. Now, to understand microscope and telescope, two things you'll have to know very clearly. The first thing is that near point. This you'll have to know. Near point of our eye. Near point of eye. Near point of an eye is the least distance that our eye can see distinctly, and its value is 25 centimeter. 25 centimeter. That means if you keep an object at a distance of around 25 centimeter, then we can see the things distinctly. This is also known as the least distance of distinct vision. We represent it with this capital letter D. The next thing is that far point of a normal eye, far point of a normal human eye. This far point, when we say, every individual will have different distances far point to see. So we say that far point is at infinity. For a normal human eye, the far point is at infinity. The farthest distance that our eye can see, that we call it as the far point, and it is taken as infinity. Now, after knowing these two terms, let us discuss about microscope. Microscope is an optical instrument that is used to magnify the object. The image will become larger than the object, then it will magnify it, it will make it bigger, and then we can see the image distinctly. Or the optical instrument, we call it as microscope. Again, microscopes are also of two types. One we call it as simple microscope, and one we call it as compound microscope. In simple microscope, we use a single biconvex lens, and in compound microscope, we use two convex lenses. Let us see first about simple microscope. This is a single biconvex lens. This is your principal axis, and as you know that in case of lens, two spherical surfaces are there. So there will be two focus and two center of curvature. Let me mark it as F and C. When I keep an object near to the lens, let me mark this object as AB, the size of the object. The ray that will go parallel to principal axis will pass to the focus. The second ray, if I draw passing to the optical center, then the ray will pass undeviated. These two rays, if you produce it backwards, then it will appear to be coming from a point here. If I draw a perpendicular image here, then I'll mark it as A dash, B dash. This will be the final image of the object. This is how it works. If I keep my eye here and look at this object, placing the convex lens nearby, then I can see the image in a larger way, in a magnified way. So this is how a simple microscope works. Now let us see the terms associated with it, how we can find out its magnifying power. In microscope and telescope, we don't say the magnifying power as linear magnification or lateral magnification. We use the term angular magnification here. Angular magnification or we call it as magnifying power. Angular magnification or magnifying power we define like this. the angle subtended at the eye by the image as seen by the microscope. This one if I mark it as beta, and the angle subtended by the eye while looking the object when the object is kept at a least distance of distinct vision. This distance we call it as this distance of distinct vision. This object, if I place it here at a least distance of distinct vision, then it will appear like this. Let it be A dash is already there. I'll mark here B dash dash. Then the angle subtended by our eye at the object without using the microscope, this angle will mark it as beta. This is the angle subtended by our eye while looking the object when the object is placed at a distance of distinct vision. This angle we take it as alpha. So this beta by alpha gives us the angular magnification produced by a lens. Beta, like this you can use trigonometry here. While looking the final image, which is here, so you take this triangle O, B dash, A dash. In triangle O, B dash, A dash, tan beta, it is defined as perpendicular. This one is A dash, B dash, divided by base, that is A dash, O. And while looking at the object, when the object is placed at this distance of distinct vision, then this is the object A, B dash dash, then you get this angle alpha. So you take this triangle A dash, O, B dash dash, or B dash dash, A dash, O. In right triangle, A dash, B dash dash, O. You can find tan alpha. Tan alpha is equal to A dash, B dash dash, A dash, B dash dash divided by A dash, O. Now this A dash, B dash dash is equivalent to AB because this is the same object, you're keeping it here. So this one I can write it as AB divided by A dash, O. Now for small angles, as we know, for small angles, tan theta we take nearly equal to theta. So this tan beta can be written as beta is equal to A dash B, B dash divided by A dash O, and alpha can be written as AB divided by A dash O. Now if I put the values of alpha and beta in the above equation, then I'll get the angular magnification M as beta, it is A dash B dash divided by A dash O divided by alpha. This one you are going to divide, so if you do multiply it will become upside down. A dash O divided by AB is A dash O, if you cancel it out, then your angular magnification M will become A dash B dash divided by AB, and this you already know while deriving the expression for magnification of a lens. A dash B dash is size of the image. This is HI divided by HO, and that is equal to, in lens we know that it is V by U. So magnification can also be expressed as image distance divided by object distance. Your image distance here is A dash O, and your object distance here is this one, AO. So this also gives us the angular magnification. Now two special cases you learn here to get the relation. First of all, the diagram which is available to you, you can see case 1. When the image is formed at near point, The diagram that you can see here clearly, that the image, final image is formed at the near point, that is the least distance of distinct vision. In that case, the expression for magnifying power, how we can write, let us see. We know that 1 by V minus 1 by U is equal to 1 by F. This is our length formula. From here, multiplying both sides by V, if you do, you'll get one term here, V by U. That will give you your magnification. Multiplying both sides by V will get V by V minus V by U is equal to V by F. Now V by V is 1 minus V by U, you can see this magnification, M is equal to V by F. So minus, if you bring this side, plus M is equal to 1 minus V by F, 1 minus V by F. So M is equal to 1 minus the value of V, you can see in the diagram, it is equal to D. That is the least distance of distinct vision, is towards the left hand side of our lens. So it will be minus D divided by F. So M is equal to 1 plus minus is plus D by F. This is the indoor magnification produced by a magnifying glass or simple microscope when the image is formed at near point. When the image is formed at infinity, when the image is formed at infinity, that is also called under normal adjustment. Normal adjustment. In this case, we can move this lens towards us. If we bring a little bit towards us, then if we keep the object at the focus, then you get the image at infinity. This way you can draw and show. If I keep the object at the focus, the ray that will start from the object, it will pass to the focus. Then the second ray, if it passes to the optical center, it will just go straight. These two rays, they will be parallel to each other. If you look the image from here, you will find that the image is formed at infinity. This side, it will be still parallel. Image will be formed at infinity. When the image is formed at infinity, we know that image distance V is equal to undefined. Then in this case, your beta will be this one, beta, and alpha. Alpha, when you keep the object at the least distance of distinct vision and remove the lens, that means you look the object keeping here, suppose this is A dash, B dash, the object is brought here at a least distance of distinct vision, and then without using the lens you are looking the object, then it will look like this. This will be alpha. So now if I use the formula, as we know, tan beta is equal to beta only we are going to take, so directly you can take it beta. Beta is equal to perpendicular by base for looking the final image. But here looking the final image, you cannot get a triangle. So what you'll do, you will see this one, this right triangle, B F O or B A O. It will AB by AO. it will be AB by AO or FO. So AB by FO is equal to the focal length F, and alpha it will be this right triangle A dash B dash O. If you write down, it's better in triangle ABO. This one is in triangle ABO, and this one in triangle A dash B dash O. Alpha is equal to A dash B dash divided by base is A dash O, and this is A dash B dash divided by A dash O is equal to your least distance of distinct division, that is D. Then if you find the magnification, as it is the ratio of beta and alpha, beta is equal to AB by F, and alpha is equal to A dash B dash by D. I can write D by A dash B dash. Then this one you will get like this. AB and A dash B dash, since they are both equal, in the diagram you can see A dash B dash and AB, their heights are equal, so you can cancel it. So you will get the angular magnification M as D by F. This way you can find out the angular magnification when the image is formed at infinity, that is under normal adjustment also we say. Now let us discuss about compound microscope. In compound microscope we use two lenses. One is called the objective lens that faces towards the object, and one is called the eyepiece lens that focuses towards the eye, that we see with the help of that eyepiece lens. This is your objective lens. Let us draw the lens one by one. Suppose if I keep an object in front of the lens, suppose this is the object AB, this is the focal length of the objective lens. I'm writing principal focus of the objective lens, capital FO I am using. The ray that will pass through the lens parallel, it will pass through the principal focus of the objective lens FO. It will pass like this. The second ray, if I allow it to pass through the optical center, then it will just pass straight. The moment they come and meet each other, one real inverted image will be formed. This one I am marking it as A dash B dash. This image that is formed by the objective lens will be further magnified by the eyepiece lens. The eyepiece lens is of larger aperture and larger focal length compared to the objective lens. This is your eyepiece lens. In this case, the focal length will be more, it will be somewhere here FE, the principal focus of the eyepiece lens. Then, how it magnifies, let us see. The first ray that will go parallel to principal axis will pass through the focus. This distance, you have to maintain it. If I take at an equal distance focus, principal focus of the eyepiece lens, then it will go this way, passing through the principal focus, and a ray which passes through the optical center, it just passes straight. So what happens, these two rays, as they are diverging, they will never meet each other. This side will have to produce the rays, and then you will get a point from where it will appear to come out these rays. This position where they come and meet gives us the final image of the compound microscope. So look, this one as A dash dash, B dash dash, I am marking it. So like this we get the final image. Now if you look from here, if you keep your eye here and look, then this small object that you kept in front of the objective lens will appear to be enlarged. It will be enlarged twice. AB is enlarged by the objective lens as A dash B dash, it became big. Again A dash B dash, the image which is formed by the objective lens will behave like an object for the eyepiece lens, and the final image will be formed at A dash dash B dash dash at a least distance of distinct vision D. So you have to remember that two lenses will have to use for compound microscope. Objective lens must be of shorter focal length and eyepiece lens must be of larger focal length. You can see the focal length from here to here, this distance is more as compared to this distance from here to here. Now let us discuss about this is a working for angular magnification. Let us see how to define it. The definition will remain the same as we used in simple microscope. It is the angle subtended at the eye when seen at the final image. The angle subtended at the eye while looking the final image. This one, this is beta, divided by, it's a ratio term, divided by the angle subtended at the eye when this microscope is removed and the object is brought at a least distance of distinct vision. When you keep the object here, this AB, if I keep it here, let me mark it as B triple S, A dash dash, B dash dash. This one I brought the object here, and then I am visualizing from this point at the top of the object. This angle we mark it as alpha. The ratio between these two, beta and alpha, gives us the angular magnification. So to get the expression for angular magnification, we'll have to find alpha and beta. To find out beta, we can take triangle A dash dash, B dash dash, O. In right triangle, A dash dash, B dash dash, O. Then beta can be defined as perpendicular. Perpendicular is A dash dash, B dash dash, A dash dash, B dash dash, divided by base is A dash dash, O. Base is A dash dash, O. And you can define tan alpha in triangle A dash dash, B triple dash, O. In triangle, in right triangle A dash dash, B triple dash, O. You can define tan alpha. Tan alpha, it is equal to A dash dash, B triple dash, A dash dash, B triple dash, divided by A dash dash, O. A dash dash, O. For small angles, we know that tan theta is nearly equal to theta. So we can replace tan from both the places. So therefore beta will become A dash dash, B dash dash, divided by A dash dash, O, and alpha will become A double dash, B triple dash, divided by A dash dash, O. Now A dash dash, B triple dash is also equivalent to AB, the side of the object. So we can write it as AB by A dash dash, O. Now angular magnification or magnifying power M, it is equal to beta divided by alpha. So put the values. Beta value is A dash dash, B double dash, divided by A dash dash, O into this is divided by alpha, but if you multiply it will become upside down. A dash dash, O divided by AB. Now these two terms you can cancel it out and you get like this, A dash dash B double dash divided by AB. Now what we'll do here is, we'll divide one term, common term, we'll divide and multiply by a common term. What is A dash dash B dash dash C? It's final image. Who has produced the lenses? Eyepiece lens has produced. So the final image divided by A dash B dash, if you do, that is the object for the eyepiece lens. Then we know that it is magnification produced by the eyepiece lens. So this A dash dash B dash dash I am going to divide by A dash B dash. And if I divide, then I have to multiply by the same term A dash B dash divided by, this is AB. So this term we have to introduce it. Then what you will get is magnification produced by a compound microscope is equal to, this is the magnification produced by the eyepiece lens. Magnification produced by the eyepiece lens. And this is the magnification produced by the objective lens. Here objective lens, how we know? Because A dash B dash is the final image of the objective lens and A dash AB is the object for the objective lens. So it is ME into MO, or we can remember like this: the final magnification produced by a compound microscope is the product of the magnification produced by both the lenses. Earlier we discussed about that when two or more than two lenses are in contact or nearby to each other, then the equivalent magnification is the product of magnification of all the individual lenses. So this relation you will be using it now to get the expression for magnification when the image is formed at a least distance of distinct vision, as well as under normal adjustment when the image is formed at infinity. Now let us see one by one. Magnification produced by the eyepiece lens, ME, that you already know. It's exactly like a simple microscope. You just kept inverted, you can think. So case 1, when you do, when the image is formed at near point, that is at a least distance of distinct vision, magnification produced by the eyepiece lens ME is equal to 1 plus D by F, but here the focal length will be focal length of the eyepiece. Now let us see what is the magnification produced by the objective lens. To find out the magnification produced by the objective lens, we'll use this relation. We know that 1 by V minus 1 by U is equal to 1 by F. So this is purely for objective lens we are doing. For objective lens. So here we put image of the produced by the objective lens, image distance and object distance of the objective lens, focal length of the objective lens. So multiplying by V0 on both the sides, we get V0 by V0 minus V0 by U0 is equal to V0 by F0. This will give us 1 minus V0 by U0 is the magnification of the objective lens. We can write it as MO is equal to V0 divided by F0. Now magnification M0 minus, if I write it as plus, this term plus will become minus, and this plus, if you bring this side, it was supposed to be minus, but it will become plus. Like this you can find out the value of MO. After you find out the magnification produced by the objective lens and magnification produced by the eyepiece lens, these two if you put it here, then you will get the final magnification. So the angular magnification or the magnifying power M is equal to MO into ME that we derived here in equation 1. You put the values. MO is equal to magnification produced by the objective lens is 1 by V naught by F naught, and here ME is 1 plus D by FE. So this will give us the expression for magnifying power in a compound microscope when the image is formed at the near point. Now let us see case 2 when the image is formed at infinity. To produce the image at infinity, we call it as normal adjustment. You need to adjust it, the microscope. How do we adjust? This eyepiece is movable. We can move forward and backward. In this case, this eyepiece is of larger focal length, so we'll have to move backwards so that the image which is formed by the objective lens exactly produces the image at the principal focus of the eyepiece lens. If I move the lens, then you know that its focal length also will move like this. So that adjustment, we call it as normal adjustment. Let me draw and see. It will look like this. This is the object, suppose, objective lens. This is a refracting plane. This is the optical center. So take the object, let AB be the object, and start your ray diagram. It will pass to the principal focus of the objective lens. The second ray, if it goes through the optical center, then it will just pass straight. The two will come and intersect at a point. That point will be the formation of image. Here the formation of image. Now this image must exactly form at the principal focus of the eyepiece lens. Let it be A dash, B dash. After that, you draw the eyepiece lens. Suppose this is my eyepiece lens, larger aperture, larger focal length. If I draw a refracting plane this way, this is the optical center. The ray that will go parallel to principal axis will pass to the principal focus of the object eyepiece lens. This is your eyepiece lens. This will be your FE. It will go through the eyepiece lens, principal focus of the eyepiece lens. The second ray, if I allow it to pass through the optical center, then it will just pass straight. These two rays, you can see that they are exactly parallel to each other. Then the final image will be formed at infinity. It will remain parallel here. It will look like this. Now in this case, if you are looking from here, keeping your eye here, then you can see the final image at infinity. The image will be formed at infinity. So now, here to get the expression for magnifying power, first of all, the magnification produced by the objective lens MO, we will write down, that is equal to image distance divided by object distance of the objective lens. Object distance of the objective lens is here, and image distance of the objective lens is here from A dash B dash to the lens. This is V0. So you get it like this. And in case of simple microscope, you learn that if the lens is kept under normal adjustment in a simple microscope, the magnification is given by, and here your adjustment is done in the eyepiece, so it's acting like a simple microscope. It is D by F. Now the focal length of the eyepiece is FE we are writing. So magnification produced by the compound microscope when the image is formed at infinity, that is your magnifying power or magnification M is equal to MO into ME. MO, it is this one, V0 by U0 into ME is D by FE. Here you have to take one assumption that you have to take is when the object is taken very close to the principal focus of the objective lens, and if the object is taken very close to the principal focus, here principal focal length you can see here is somewhere here, suppose FO. If it is, the object is taken very close to the principal focus of the objective lens and the image formed by the objective lens is very close to the eyepiece lens, then this image distance can be taken as the length of the tube of the microscope, because if the image is formed very close to the lens, this distance from eyepiece lens to the objective lens, we call it as length of the tube. So we can write V0 as, V0 can be written as length of the tube, and U0, this object distance, will be nearly equal to the focal length of the objective lens, and it is on the left hand side, not the right hand side one, it's on the left hand side. So we take U0 as minus F0. Then in that case, your magnification expression, therefore M, it will be minus L by F0 into D by Fe. This is the final expression for the magnification produced by a compound microscope when the image is formed at infinity, that is under normal adjustment. So you need to be very careful. You start with this, then you take this assumption. After that, you write this one while deriving. Thank you and have a nice day. Stay tuned with LFI Educate.